Number 4 is what? Oh, cone gravity. I mean, I listen to a lot of rock and stuff, so I have a bunch of tritium, sevenfold. I'll take that.
I know a couple actually. Yeah, my mom's.
This stuff I play guitar a lot. What's the player again? What's the player? So we're going over?
Oh, I know. I don't know.
And there's like my top one. Yeah, definitely.
Okay, good morning everyone. Good morning. Good morning. First things first, your midterm exam is closed. It closed last night at 11:59 p.m. Wait, what? Alright, hopefully you got to write your exam. Well, I was wondering what your thoughts are on the exam after you finish writing.
Crushed it.
Say it again.
We crushed it, yeah.
Let's see, that's nice to know. Was it fair, you think?
Yeah, fair.
As I said, it was straightforward. Right? Did the extra time help?
Yeah.
No stress?
There was stress on the exam.
Bro, got on like 3 hours later.
Yeah, actually, I did.
Oh, Marky's actually funny for one time.
Yo, the camera did it.
Okay, calm down. Yeah. That's a pretty good one. But hopefully it was not a painful experience. Okay. I will have your exams graded. As you know, I'm the one who grades all these exams, especially. I will have them graded in some time, and hopefully by the end of next week you should have your scores done. Okay. All right. So we will continue with our journey into shear force and bending moment, diagrams and stresses. So today, as I said, I have a problem with some numbers. Okay, just to put some perspective on what we've been doing so far. Okay, so here is the figure I'm going to draw. Then I'm going to talk about the cross section of that beam that I'm going to be drawing, and then I'm going to spend at least 20 minutes obtaining the moment of inertia. This is going to be slightly boring. Calculation of moment of inertia is pretty tedious and boring, but it has to be done. Okay? So I appreciate your patience as we go through it. I'm going to do this only once. This one time that I'm doing this problem. From next time onwards, I will put up on Carmen, and I said I will put up like centroid derivation as well. One of you asked me last class, and I'll do that soon. I'll put up some moments of inertia for common cross sections that we will encounter in this course. I just want to do this one time to remind you of what you did in statics, or what you may not have done in statics. Okay? So here is a problem. So I have a simply supported beam, so pin on one end, a roller on the other end. And here are the loads that are acting on this body. Okay, so this is a beam. Okay, I have a uniformly distributed load of magnitude 150 pounds per feet. This is acting over a span of 6 feet. This is A, B, Okay, then I have a 2 feet gap where there is nothing going on. Okay, then towards the end of the beam I have a triangular distributed load which is sloping down, starting from a maximum and then sloping down. So this is shown in the following manner. The magnitude of this is 200 pounds per feet. Right here. 200 pounds per feet. This is over a span of 6 feet. Of course, not down to scale. You are told that the cross section of this beam is a T section. Okay, so the cross section I'm going to draw it separately. So in reality, if you look at any problem, the cross section will be drawn right next to the beam itself. So something like this. Okay, so this would be the cross section, but I'm going to draw it slightly bigger because it is helpful. Okay, so here is my cross section. This is called the top flange of the beam. Okay, so the top portion is called the top flange of the beam, and then I have a web. Okay, which is the vertical piece. And here are the dimensions. So this is the web, flange, and in 3 dimensions, you will be seeing this throughout the length of the beam as the cross section. T sections, L sections, and I sections. We will see that as I solve more problems, why we use these kinds of cross sections. Why does somebody randomly get up in the morning and say, okay, I'm going to design a beam with an I section? Makes no sense, right? There is no symmetry of any sort in this, in terms of stresses and so on, but there is a reason behind it. Okay, we're going to get there slowly. Here are the dimensions. So the web has a thickness of 1 inch, the flange has a thickness of 1 inch as well. The height of the web is 3 inches. And the width of the flange is 4 inches. Alright, what do we need to do in this problem? We need to find sigma max and tau max transverse shear stress to obtain. Sigma max due to the bending moment. Okay, so this is bending stress. Tau max transverse shear stress, and specify where along the length of the beam and at what point on the cross section these values are. Okay, so specify where they occur along length of the beam and at what point on the cross section. Like you have done for shear stress due to torsion, we would have seen that the shear stress, maximum shear stress location has a certain location along the length of the shaft. Then if I look at the cross section, any point on the outermost circumference is going to be the maximum shear stress location. So same idea here as well, nothing different. And immediately the light bulb should go on in my mind that if I'm asked to find sigma max and tau max, I need to find V max and M max. The maximum shear force, the maximum bending moment. Okay, so in effect, I need to find M max and V max, and the best way to find M max and V max is by drawing the shear force and bending moment diagrams, which we will be doing soon. Okay, so these are the two things that we need to find out. And we obviously know that in order to find out these bending stresses and shear stresses, we need to obtain the moment of inertia about the neutral axis. Okay, so to do that, we need INA. So I need this. I need this. And I need that. These are three things that I need to find out sigma max and tau max. Alright. My first order of business is to figure out where the centroid of the cross section lies. I haven't set up an axis system yet. You'll see that very soon. I want to find out where the centroid lies, and I want to find out what the moment of inertia is about the centroidal axis. Okay, so my aim locate the centroid of the cross section and then obtain moment of inertia about the centroidal axis. The centroidal axis is the same as the neutral axis. So this helps locate the neutral axis. Then what is the moment of inertia about the neutral axis? Moment of inertia, shorthand notation, about the centroidal axis. So we will do these calculations for this one particular cross section, and then the rest of them is just rinse and repeat for different other types of cross sections, so we don't need to spend time doing that. Here is how I do it to calculate centroids and moments of inertia. I urge you to follow this particular procedure because it's simple. Okay, in my opinion, it's simple. The first thing I do, after you've copied down the problem statement and so on, the first thing I do is I choose some point on this cross section and I set up a pair of axes. I want to choose a point on the cross section such that if I'm measuring the distances from that point, I want all my distances to be positive values. Okay, so from that perspective, I'm going to choose this corner point. You can choose any corner point if you want. And I'm going to draw a pair of axes there. So I'm going to call this as the y-axis for the time being. Then I'm going to have another axis which I'm going to say perpendicular to the y-axis, z-axis. Okay, so what did I do? I chose a point on the cross section, some random point on the cross section. You can choose a point in the center of this piece as well. It really doesn't matter. Okay, the math should find out what you're doing if you're doing it properly. Then I set up a pair of axes, y-axis and z-axis in this case. Then I locate the centroid of each of these simple shapes. Okay, so you will see that this is a composite body, right? This is a collection of two rectangular shapes. Okay, so this is a composite body. I want to maybe write that somewhere here. So this is a composite body. You break that composite body into the minimum number of simple shapes. What is a simple shape? A rectangle or a circle or a triangle. Okay, this is typically how finite elements also present. So we are taking a clue from something that's very nice. So break it into minimum number of simple shapes. And in this case, I can break it up into two simple shapes. Okay, so that's the smallest number of shapes that I can have. I will call the first shape as 1 and the the second as 2. Okay, so this is going to be called as 1. This is shape 2. As you might have done in statics, here is my next step. I locate the centroid of shape 1. I locate the centroid of shape 2. What is the centroid of a rectangle? Right at its center. Really silly, right? So I locate the centroid of the first one. I call that point C1. Then I locate the centroid of the second one, which is C2. And all I'm doing now is from the origin, so this is going to be my origin O, okay? From the origin, I figure out what is the distance of this point C1 and C2 about the x-axis and the y-axis and the z-axis. Okay, so I will mark these distances starting from here. If the thickness is 1 inch, then this is going to be half an inch. And I'm going to call these as y bar 1. Which is the y location of the centroid of the first simple shape. So the bar represents centroid. Okay, whenever I talk about centroids, it will be a bar. So this is the y location of the centroid of the first simple shape. Okay? And this might be old news to you because you might have done this in statics, but I still want to spend time doing it. Then I do the same thing for C2. I say that, okay, C2 is located here. All the way from my origin, this is important, I always look at my origin, all the way from the origin, so right here. This distance I'm going to call as y bar 2. And this is going to be half of whatever the web height was, which is half of 3, which is 1.5, plus a distance of 1 inch, so this is going to be 2.5 inches. Okay, so I have y bar 1, I have y bar 2. Likewise, I'm going to do the same thing about the z direction, so I'm going to have a z bar 1 and a z bar 2. Okay, starting from the origin O, all the way to the point C1 and C2 along the z-axis. Common sense tells me that this is the same thing, which is equal to 2 inches. Okay, so starting from here. Right, so this distance from the origin along the z-axis, z bar 1, it's also the same as z bar 2. And this is equal to 2 inches. Any questions so far, please? Alright, then I write the area of cross section of each of these rectangles, which is height times width. So A1, watch this. Of course, this is kind of silly, but what is base and what is height? It depends on the axis perspective. So according to the axes that I have set up, the base is going to be 4 inches for the flange, the height is going to be 1 inch. Okay, so this is going to be B1, H1, which is 4 times 1 inch square. Okay, then A2, which is B2, H2. What is the base for the web? 1 inch. Okay, so 1 times the height of the web is all the way from the bottom to the top of the web, which is 3 inches. So many inch square. Okay. All of this information will be helpful to me in obtaining what the centroid location is, and this is obtained by using the area weighted averages, like you would have done in statics. Okay, so y bar, the main y bar, which is the location of the centroid of this cross section with respect to the origin that you have drawn, is given by the area weighted average. Y1 bar A1, Y2 bar A2. If I have 3 pieces, there will be a Y3 bar A3. If I have 25 pieces, I keep writing this summation until I end up all the simple pieces. divided by the net area A1 plus A2. Likewise, Z bar is Z1 bar, Z2 bar, A1 plus A2. And importantly, Y bar and Z bar are the location of the centroid of the cross section with respect to the origin O. So Y bar, Z bar locates centroid of the cross section, centroid of the composite shape, with respect to the origin at O. Your origin need not be the same as mine. Okay, you can choose any point as your origin. I have chosen the point O, so that my distances y1 bar, y2 bar, and z1 bar, z2 bar come out as positive. If I had chosen, for example, this point as my origin, then I would automatically, I guess this point is also not too bad, but if I had chosen maybe this point here as my origin, depending on how my axes are set up, I would end up getting z1 bar and z2 bar to actually be negative 2 inches. That has to be carefully taken into account. So choose an origin. You have seen this in statics. Sorry to bother you or bore you, but this is important. Choose an origin such that your distances y1 bar, y2 bar, z1 bar, z2 bar come out to be positive. Keep track of all these fellows. Do the substitutions here. You'll end up getting the following. 1.36 inches, we have all the values there. This is common sense. Z1 bar is the same as Z2 bar, so I take it out of the bracket as a 2 inch, and A1 plus A2 in the numerator denominator cancels off, so this is 2 inches. If you see symmetry in a problem, you don't need to do this calculation here at all. Okay, so in reality I don't need to show this calculation. I can just look at the beam, okay, say this is where the symmetric z-axis is going to be. The only thing is where is the y-axis located. Okay, so that's kind of tricky. Any questions please so far? Yes sir.
Does it really matter if you go y bar z prime or z bar y prime? Because now how we're treating it as x, y. So we're substituting z for x, and usually x goes first. Does it matter?
You mean you want to calculate this first and that next?
Yeah, like when you write the centroid, does it matter if we keep it as y, z, or can we change it to z, y?
To z, y.
Yeah.
Oh, you mean this
Yeah.
Oh, that doesn't
doesn't
matter.
matter.
That doesn't matter. Yeah, I'm not going to be using that. I'm going to be using the physical body as a reference. So here is the deal. So I found out that y bar is 1.36 inches from the origin O. So starting from here, so somewhere here, which is at a distance of 1.36 from the top flange. Is going to be my y bar, and then obviously my z bar is sitting right at 2 inches, so I don't need to do anything there. And so I set up my main centroidal axis now. This is my main centroidal axis, and if you want you can call this as z bar. I'm going to draw a new figure where I'm going to unpack all of these things. And as I said, this is the only time I'm going to go through these calculations slowly. Next time onwards, we will just say we know how to do these things. Okay, you will see some in recitations as well. Alright, any questions please? Okay, and typically I call my main centroidal axis, so this is the centroid C. And not to get confused with the y and the z axis that I've already drawn, so I will just call this as y bar axis. And this guy is the z bar axis. Okay, that's not the same as the value of y bar and z bar. Okay, there is have to be some room for confusion there, but that's not That's not the case. I'm going to push this thing up. Sure. All right. Okay. So now my next aim is to calculate the moment of inertia. Okay? Yes, sir.
Shouldn't your y-axis been the one going up, and then your z-axis being the one going to the right?
Right. I mean, you can call them by any name. That's completely fine. But I'll follow what you said. So I should really be calling this as a z-axis, but it doesn't really matter because they are different from the main axis that I've chosen. Okay. So, but that is fine. I think we will call them by the way you suggested. So here I'm going to draw the shape again. I'm not going to draw everything there, just a few things. Okay. Centroid of each of these shapes. C2, C1. Centroid of the main creature is C. Now for each of these I'm going to draw a pair of axes. Okay? You can call them by whatever name you want. If you call them by a particular name here, then you have to be careful how you refer to it on the beam axis. Okay, so if I choose, as you said, I'll choose the z-axis to be here. Okay, so this I'm going to call as the z-bar axis, the main centroidal axis. Y-bar axis, and I'll do the correction there as well just to be consistent, but it does not really matter. I could come and call this as alpha, and I could call this as beta. It's just an alphabet. Okay? The way I choose my third axis depends upon the right hand rule. So if I go from the y-axis to the z-axis, the x-centroidal axis is passing through the center of the cross section, but not the centroid of the cross section, but into the page. Okay? For the other two, I'm going to call this a Z1 bar. I'm going to call this a Z2 bar, and the y-axis for each of these are coincident with y bar. Okay, so if I complete it, this is the same as y1 bar, y2 bar. These are all axes. I already know according to the origin where my y bar is sitting. Okay, so first of all, I have the first centroid, which is y1 bar, right here. Then I have the second centroid, which is y2 bar, all the way down. And I have y bar. Okay, so these are all distances. These are all axes. These are all distances. You don't need to show any of these things. It is sufficient if you just show that one particular figure there. I'm just drawing it for the sake of simplicity. Okay, nothing else. And if you want, you can show your z bars and so on too. So z1 bar, z2 bar is equal to z bar. Okay. Then we calculate the moment of inertia. Now the moment of inertia can be calculated about either the z bar axis or the y bar axis. Sometimes I might need both. Sometimes I might just need only one. Okay, so moment of inertia about the y bar, z bar axis. For this you have to use a parallel axis theory. Let me start writing out what the moment of inertia is for the z bar axis. Okay, so I call this as I ZZ. Okay? Here is how we do it. This was our first shape. This was our second shape. The moment of inertia about a neutral axis is the moment of inertia of the first shape about its centroidal axis, plus the parallel axis theorem inclusion, which says that its area of the first shape multiplied by the distance between the two parallel axes. Okay, so I'm going to label that distance here as a distance d suffix y suffix 1. D is a distance, common sense. Y is distance along the y-axis. And 1 refers to the fact that this is the distance between the first Z1 shape and the main centroidal axis. Make sense to everybody? Just a form of notation. Okay? So this is now going to be I Z1, moment of inertia of the first shape about its centroidal axis, plus area times the square of the distance between the two. This is the parallel axis theorem. This entire thing is the parallel axis theorem. Plus, if I have 20 shapes, I have to do this for each of those 20 shapes. I Z2, which is the moment of inertia of the second shape about its centroidal axis, plus the area of that. And parallel axis theorem of that. Do you recall doing these in statics? Okay. It's just mathematical donkey work is something that has to be done. Okay, otherwise we can't proceed with the problem. Alright, then I have to do the following, just for this one particular problem, I'll write this out. Okay, so IZZ is the following. Always remember for a rectangular cross section, so I'll write that here, so remember. If I have a rectangular cross section, if I have the centroid of the rectangle which is right at its center, then my moment of inertia about the z-axis is the base 112 times the base times the height cube. Okay, this is something that should have been derived in statics, so I'm just going to present the results. Please remember this. Okay, IYY is 112. HB. Okay, this is for a rectangular shape. So the base axis is always the axis parallel to the horizontal. The height axis is the axis that is parallel to the vertical. Okay, the distances. And all I'm doing is applying that formula to our problem right here. So let me do this methodically. So I Z1 is 112 B1 H1 cube, where B1 is the base of the first flange, which is 4 inches. H1 is 1 inch. Okay? Plus the area of the first shape, which is B1 times H1, rectangle, right? Multiplied by the square of the distance between the two parallel axes. You look at the distance. What is that distance going to be? It is going to be this y bar minus y1 bar whole square. Okay, once again, the distance is this distance between the two axes. It is the total distance y bar from the origin minus the small distance of y1 bar. Okay, so this is going to be y bar y1 bar whole square. This is for the first shape, plus 112 B2 H2 cube, where B2 is the base of the web, is 1 inch, H2 3 inches. People in the back, can you see my writing? Okay. V2H2 cube plus area V2H2 multiplied by the square of the distance between the parallel axes. In this case, y2 bar is greater than y bar, so it's going to be y2 bar minus y bar whole square. And even if you make a mistake there and say it's y bar minus y2 bar, you're squaring it, so you're all in good shape. But please don't do that. Does this bring back memories? No? Okay. Yes, yes and no? Okay. No. Hopefully you are not in my statics class, the people who are saying no. But I can certainly understand these are things that you need to be doing often to keep it on top of your mind. Okay? You're going to be doing this pretty often from now on. Alright, this is just, as I said, grunt work. Substitute the numbers, and I'm going to end up with the following. So IZZ is IZZ1 and all that. I'm going to leave the substitution to you, but please check the numbers. This is what I'm going to end up with. 9.44 inches to the power 4. Okay? Units, please be careful. Please be careful. Units, length times length cube. So length to the power 4. It's either going to be inches to the power 4 or millimeters to the power 4. If you have a cross section given in inches, keep it in inches. If you have a cross section given in millimeters, keep it in millimeters. If you have a cross section given in feet, convert it into inches. Okay, because the cross section obviously is going to be the smaller of the dimensions compared to the length. Length is the largest dimension. Okay? I can also do IYY. Let me do that quickly. I actually don't need to do it for this problem, but you'll see. IYY is the problem. Same principle. Okay? I'm just belaboring the same point, but here it is. So this is going to be y1, A1 times the distance between the z bar axis and the z1 axis. What is that distance here? Distance between the z bar axis and the z1 axis.
0.
Is 0. There is no distance, right? Absolutely. But I'll just write this as the following. So d z1 square, this is that distance, square that distance. First parallel axis theorem, and then second shape. Distance between the z2 bar and the z bar axis, which is also 0 because they're all coincident. These are distances between axes, which is why it's called the parallel axis theorem. And these are all axes that are parallel to each other. Parallel axis theorem is really important in dynamics, in mechanics of materials. Why is it important? It's because it simplifies your life. That's all it is. Okay? Alright, y1, y2, y2. So for us, these distances are 0 in this problem. Okay, this is in this particular problem. This is not in general, please. Right, and y1, y2, y2 will be the ones that will be left for me. I, y, 1 by 12. H1, B1 cube. Remember the formula? Okay. Plus 1 by 12 H2, B2 cube. Plug in these values, and this is what you'll end up getting. I actually did not calculate it, so you can calculate it. Okay. Once again, first and last time I'm going to be doing this in this class. If you have any questions on this concept, please stop me right here. As you see, it eats up time. Are there any questions, please? Please don't hesitate. Yes, sir.
In the first IZZ equation, is there supposed to be a plus sign between those two expressions?
Oh, yes, absolutely. Yeah, thank you for pointing it out. Right, it's a plus sign. Thank you. Yes, yes.
So dy1 and dy2 are just the distance between that centroid we found and the centroids of each.
Absolutely,
separate shape.
absolutely. Along the y-axis.
Right, well, yeah.
Along the y-axis. And the same thing for z2 bar and z2 and dz1 are distances of the centroids about the z-axis. And they are 0 because they're all coincident.
Same line, yeah.
Absolutely. Yes.
Can you draw dy2 just to make sure? It will go from the z1.
Oh, dy2 is going to be this one.
Okay.
Thank you for pointing it out. I think I missed out on that. Yeah, dy. All right. So, okay, now I'm going to draw the shear force bending moment diagram for this problem, and then we'll come back in the next class and wrap it up, and then I'm going to start doing three-dimensional loading. Okay? All right. So keep all these numbers in mind. Can everybody see if I write here?
Yes.
Okay. People in the back. If I start writing here, will you be able to see? All right. So shear force and bending moment diagrams. Next time. This is how I usually start solving these problems. First, find out the groundwork stuff, moment of inertia, centroids, and so on. Then you draw the shear force bending moment diagram, which is much more elegant because we're using this graphical method. And then lastly, we will be using the formula to find the stresses. That's the easy part. Okay? You've got to calculate the support reactions, which I'm not going to do. Okay, so please do that. Then here's my free body diagram. I'm going to have AY, vertical support reaction. I'm going to have BY, which is another vertical support reaction. Here are the values. These 878.6, right? Let's say 878.6 pounds. And then BY ends up being 621.4 pounds. AX is 0. Okay. If you want, you can write it out there. Then I write back the distributed loads and so on. £150 per feet, 200 pounds per feet, 6 feet, 2 feet, 6 feet. And as we said, we are not going to be doing extensive calculations because we are going to be employing the graphical technique. Okay, I'll give a pause. I want to finish off drawing these figures for the day, and then we'll come back and finish off the bending stress calculations next class. All right. Now you guys are going to help me draw it. I'm starting with the shear force then. Okay, so 0, x in feet. This is V in pounds. This is a good refresher because it's been maybe some time since we looked at shear force bending moment diagrams. You had your exam, and so that might have become a little bit of a back burner thing. So how do I start? I start by looking at the support reaction, right? So my support reaction will scoot me up. Okay, so this is going to be 8.8.6. Then I look at myself and see, so 6 feet, let's write somewhere here, 2 feet, this is 6 feet, okay, so I can mark these look at myself and think, okay, this is 150 pounds per feet, which is pointing down, multiplied by 6 is 900, right? 900, which is the area of the distributed loading, is greater than 878.6, which means that this has to push me down below the negative x-axis. Making sense to everybody? This is 878.6, this area is 900, difference is around 21 or something. So that's going to be a negative value, so I'm going to end up being somewhere here. Minus 21.4. The idea is, how do I go from where I am to where I want to be? I look at the slope of the shear force diagram, which is equal to the load intensity. Load intensity is pointing in the negative y direction. Constant. So my slope is constant and negative. Okay? So I'm going to fall down this way. And you immediately should recognize, okay, hey, there is a zero crossing here. If I have a zero crossing, it signifies a special event in the bending moment diagram. It's either a maximum or a minimum. Okay, so this is a zero crossing. In this problem, it's fairly trivial to find the zero crossing using similar triangles. Okay, so if I call this distance here, that's a distance x, then the remainder of the distance, because the total length is 6 feet from where I am starting to where the minus 21.4 occurs, this is 6 minus x feet. Similar triangles. 878.6 by x is 21.4 by 6 minus x. Okay. Solve for x, which I already did, and I get it to be around 5.86 inches. So x 5.86 feet, I'm sorry. Is the point of zero. Okay. So far, so good. How do I go from where I am here to the next point over a distance of 2 feet? I don't see anything happening, so I just go as a straight line. Okay, so I just go right this way. Then I see that there is a triangular distributed load which is pointing down. So I'm going to go further negative. How do I go? My slope is negative and it is decreasing in a linear manner. So my curve is going to be a quadratic whose slope is decreasing in a linear manner. Okay, so I start at zero slope because there was no force acting, and then this is like a maximum now, or whatever the value of that is. So from there I just slope down, go to zero slope. This is going to be a quadratic. And the saving grace is I have a force which is pushing me up, hopefully. It will push me up by that amount, and one can do the calculations and verify that it is indeed the case. Okay? So this is my shear force line. Alright. Bending moment.